Hello and welcome to another video, and in this one we're going to work on building on to our ray tracer from previous lecture. And the goal of this lecture is to one, add some lighting, like ambient lighting, then refactor our code so it's easier for us to build upon in the future lectures, and then um, start adding some shadows. So let's get started. This is what we're going to try to accomplish here, what you see. But before that, I'm going to quickly show in Blender as it'll just be easier to understand. Kind of like what we're trying to go for, as in terms of trying to add shadows. So we're going to go ahead and delete our cube here. And we're going to Shift A, Mesh, Plane. I'm going to scale this to be twice this size, hopefully something like that. Shift A, our UV sphere. Let me scale this even bigger. Perfect. Then we got our UV sphere here. Grab it. Y. No. Z. Move it up. Something like that. And then we go to our render view. And hopefully that loads with no issue. And there you go. You can see got a little some lighting, and then we got our shadow here. So something like this is what we're trying to work towards. So yeah, let's move to our coding. So this is where we have left off in the previous time. Uh, so I'm gonna split it up into a few sections. First, we're gonna work on adding ambient lighting. Um, and there's only gonna be like there's gonna be like one chunk of new code. Rest is just mainly refactoring and preparing for future lectures. So first, we're gonna create a new helper function, just like the ones we have here with cross, scale, length, and normalize. This one's going to be called function element wise, and this will perform the element wise multiplication of two vectors. So we're going to pass in p1 and p2, and then we're going to do return square brackets p1x times p2x comma p1y times p2y, and then we just have z left, p1z times p2z. Alright, so that's our element-wise function. I'm just trying to do the setup first, and then once we actually get into the calculation of lighting, this will make a little bit more sense on why we included this uh, function here. So, alright, our function looks good. Next function, we're going to add another one, and this one's going to be called array to color. And it's going to convert an array representing a color to an RGB string. Alright, so let's go. It's going to do function array to color, and let me close this out. Alright, array to color. We're going to pass in C, and then here we're going to do return shift, and you have this. I forgot what exactly the name is, but um, like the backwards quote or whatever. So we're going to use that. Then we're going to RGB. Then we're going to do the dollar sign. And there we go. So now we'll get the C, and then we'll get R from it and multiply it by 255. Then we're going to do comma. Then we'll do dollar sign again. Then we'll get the G from the array. CG times 255. Finally, we just got to get the B, blue. For that, we need to do dollar sign C RGB times 255. Okay, so there you go. This is how we can convert an array representing color to an RGB string But in order to that, we need to set up these RGB constants first. So we're gonna go back up here, and where we set up our XYZ constants, we could do another line where it goes const R equals 0, G equals 1, and B equals 2. But instead, we're just gonna use the same thing, as that's just more efficient way to do it, and it just accomplishes the same thing, because we're gonna do the same way where we set it to equal to 0, 1, and 2. So, all right. So now our constants are set up we have the constants set up for the vector indices and the color channels. So next we have added our helper functions. Now let's go to our setup section, which is right here. In here, what we're gonna do is we're gonna set up our ambient light color. Do const ambient light, and now it's gonna be an array. As you can see, 0 0.1, 0 0.1, 1. All right. So that's our ambient light color. Next, we're gonna do a white directional light. So we're gonna do const light spec object. We're gonna do light direction set equal to -1, 0, 0. And then we're gonna go color, go 1, 1, 1. All right. So that is our white directional light. Next, we're gonna do an array of lights, but we're gonna just pass in our light spec that we just made. So it's very similar, as you can see, the setup for the triangles and the spheres, and then now for the lights. Follow the same pattern, so easier for you guys to follow. Um, and so now, a key thing we need to do is change these to our RGB array, like how we have. So let's just go ahead and do that real quick. 0, 1, 0. Then we're gonna go 1, 0, 0 for red. So we got green, red. Finally, we're just gonna do yellow, which is gonna be red and green. And that should be it. Let's go see what has happened to our code. Alright, it's a little bit broken. That's okay. We had our setup and everything done. So we're gonna go ahead and add that ambient lighting, you know, use that for computing our light. So what we're gonna do is first we're gonna do for the sphere. So we're gonna go down to all the way to the for loop where we calculate, go through the sphere specs in the sphere array. And here we're gonna get to the bottom where we do our fill style. So that's where the that's gonna happen. So first, we're gonna get our P. So to get that, which is the intersection point, we're gonna set that up right right after we do our check arc T continue. So we're gonna do it right here. So our intersection point for our sphere. So we're gonna let P equals add O. The O comes um, from up here when we calculate it. As you can see, that is from there, and then we are going to we're gonna get the so to get the intersection point, we go add O, scale, center R and T. So since if there is T, that's why we were able to get here. Next, we need to do let n equals normalize. We're gonna find get the normal at that intersection. We'll do normalize minus, and we'll do p, and then pass in the center of our sphere. All right. So this one we need to do it just for the sphere. Um, but yeah, once we do that, next we need to set up our arriving light. So we're gonna go right here after we get our nearest distance. We're gonna do let arriving light equals 0, 0, 0. Alright. So after we do that, um, so this is initializing the light arriving at the point. Next, we're gonna add the ambient light, and we do this by going arriving light. Misspelled it. Arriving light equals add. Use the add function. Pass in the arriving light that we initialized with the ambient light that we have initialized here. Right. So next, um, we need to add diffuse light from each light source. So in order to do that, we're gonna go use a for loop. We're gonna do for let light spec of lights that we set up above. We're gonna do let d equals dot, and then pass in light spec dot light direction and the n, which pass in the n. And so what this is doing is it's computing the dot product of light direction and normal. Then we'll do an if statement to check if our d, the dot product, is less than 0. If it is, then set it equal to 0. Then if not, then we're going to go here. We're going to scale the light color by intensity. So we're going to let light color equals scale. We're going to pass in the light spec color and our dot product. Next, we're going to add it to total light, which is arriving light equal add, and then we're going to pass in the arriving light that we calculated over here with the light color we just calculated here. And there you go. Next, what we're gonna do is we're gonna combine light with the object's diffuse color, and that's where the element-wise function comes in. Right here, we're gonna do let color equal element-wise. We're gonna pass in our arriving light and our sphere spec color. So we're gonna remove it from here in a second. Um, or just right now. So what we're gonna do is we're gonna remove that because we pass it into our element-wise. Instead, we use um, array to color function, and let's see. I'm not too positive this will work. Okay. So so you can see that right here. One thing I forgot to do was we're not gonna focus on animation in this one, so I'm gonna turn off the triangles, animation. So I'm gonna go here, comment this out. Oops. Comment that out. And then I'm gonna push the sphere away from us. I'm gonna do negative 1.45. Then I'm gonna come down here, comment this out too, I believe. Yep. So we're gonna, yeah, take care of that. This doesn't matter. I mean, yeah, okay. So let's go here. That's what we got, but we're not quite done yet. because we still need to do this for our triangle. So yeah, but the code is gonna be pretty similar. So we're just gonna copy this up until here. Copy that. We're gonna go up to our triangle spec right here. All we just need to remember is triangle spec dot color. I'm gonna type it in. Pass in the triangle spec. And one more change. That is um, for uh, for the sphere, we just did d equals 0. That's because no light contribution for back-facing surfaces. For this, we need to change this to d multiple times equals -1 because you flip the direction for double-sided objects. So let's go ahead and take a look at this, and yeah. So that's kind of what our first section is. First part here is adding that ambient lighting. So the next what we're gonna focus on is refactoring and then adding some shadows. So I know we just made these, kind of set up here to calculate, but we're gonna have to kind of redo it. So basically, we're just gonna copy this from here up until here. Yes. Copy that. We're gonna go up here, um, roll our time variable, and we're gonna put this into a function to calculate the color of a point based on lighting. So we're gonna call it function calculate color. In here we need to pass in a couple things for the parameters. One, first thing is n, which is the normal vector at the point. P, position of the point. Then the diffuse color, which is the diffuse color of the object. Like, we pass in our triangle spec dot color, sphere spec dot color. That's what that is. Next, we're gonna have double-sided equals true. So this is for when checking, if we need to flip the direction for double-sided objects, or we do no light contribution for the back-facing surfaces. So that's the parameters. We have that set up now. Just go ahead and copy paste this in here. Everything more or less remains the same, except we need to change this if statement right here. Um, we're gonna do this. So this line right here is, flips the direction for double-sided objects. But then we also have our case with our sphere, and for this, the else will take care of the no light contribution for back-facing surfaces. So yep. But then I need to, okay, need to put this in a, there we go. And then we need to put this in here. If double-sided, then you have it do that. Copy this and move it right here. Basically, if double-sided, flip direction for double-sided objects. Um, else, no light contribution for back-facing surfaces. So that's all looking good. Then we go down here, we calculate here instead of triangle spec.color, that's what I was mentioning. That's going to be passed into this function parameter, so we just do diffuse color, and then we're going to return array to color. There we go. So this function is set up, so that's basically part of our refactoring. So what we're going to do is go down here, and we're actually going to remove all this code. We don't need it, and you'll see why in a bit. I know we just typed it up, but at least this way, going through it step by step, it's easier for you guys to understand instead of for me to magically put things into functions. Instead, we gradually work through it and then refactor it into functions. So same thing goes here for the sphere. We're gonna remove all that code. And yeah, so that's one section of the refactoring, and this is pretty much the big new chunk of code that we added. Next, we're gonna make a function called cast array. It's gonna be called cast array, and it's gonna cast array and find the nearest intersection. That's what the goal of this function is to do. So let's go ahead and set that up, and it's a pretty big function, as you'll see in a bit. Cast array, and then we're gonna pass in O, which is the origin of the array, and then R, direction of the array. Uh, and then it'll return the intersection details or undefined if there's no intersection. And well, there's only a few lines of code that we're gonna write. First is let nearest n equal undefined. So we're gonna set it up to undefined. Okay. So this is the nearest n is the normal at the nearest intersection. Next one is let nearest p equal undefined. As I said, it's just our setup in this function, and this is the position of the nearest intersection. Next, let nearest spec equal undefined, and this is the object specification of the nearest intersection. And then two more lines of code. First, then we have our if statement, which is if there is no nearest spec, nearest spec, then return undefined because there's no intersection found. If there is an intersection found, then return an object with this. So we're going to do n, and this is going to be the normalize of the nearest n, and then next is going to be p, nearest p, and then t, nearest distance. Finally, spec is going to be nearest spec. So you're going to be wondering, where are we going to get this, right? What we're going to do is basically just move a bunch of code. So we're going to start actually a little lower. So we're going to start at the end of our, we have that for loop for the spheres. We're going to start at the end right here. And then we're going to copy all the way up to here, where we set our nearest distance to a max value. So we're going to copy, to track the nearest intersection distance. So we use that, right? So we're going to copy all the way up to that. Copy, and then delete. Then we're going to go up here. We're going to paste it right above this if statement. So like right after this one, where we set our nearest spec to undefined. We're going to paste that. We're going to have to do a couple tabs. There we go. But we're not quite done. We just got to add a few more lines, and that is these. We need to pass these, don't we? So that's what we're going to do right here. We're going to do nearest n equal to n. Calculated at that right there. Nearest p equal to p, and then nearest spec. We're in the sphere function here, so it's going to be sphere spec. And then we just copy these three lines and put it for our triangle as well. Only thing we need to change is this to triangle spec. And our cast ray function should be done, assuming there's no typos. last bit of thing to be done is go to a render function because uh, we set up our color function, but we're not calling it or using it, right? So that's what we're gonna do right here. Is we're gonna do let result equal. We're gonna call our cast array function here as we pass in the O and the R. So this will cast the array and compute color if it hits an object. So we're gonna check that. If result, if we are getting something, if it's not undefined, then we're gonna do let color equal calculate color function. We're gonna pass in the result, the n res from the result, and that's how it's gonna be. We're gonna put the p from the result, then same as with the result dot spec dot color, because we need to get the color of the spec, whether it's triangle or sphere. And then we're gonna just do our classic ctx dot fill style, and it's just gonna be the color that you get from there. Same as here, fill rect. We're gonna do px py 1. All right, that should be everything. So we'll see if it works in our first try. I believe that it worked. Let's go. Uh, yep, we got some shadows in here, and uh, yeah. So now our code's all refactored and ready to go for future lectures where we build upon this, add more shadows. Um, um, yeah. I hope this video was helpful. You know, breaking it into separate parts. First adding the lighting, some ambient lighting, then refactoring the code and adding some shadows. To kind of do a quick summary, you know, raise our cast from the camera through each pixel to determine the intersection with objects. Then we calculate ambient and diffuse lighting to determine the color of each pixel. And then the code checks for intersections with triangles and spheres, and the nearest intersection is used for corresponding pixels. Intersections are colored based on the object's material and objects lighting. Pixels with no intersections are left black. So yep, this is the end result that you should be obtained from this. So that's it for this video. Thank you.